You can find it on the website right here. So the first thing right here, this is what you want to download first. It's just a PDF document. It has the instructions for the project. Download the distance graph and the speed graph here. So you're going to collect some data and then you're going to plot that data. For any of the high school students, I do need a permission slip because you're going to be driving around to do this. And I won't grade it until I have that. So you can do a great job on the project, but if I don't get a permission slip from you, then I'm not going to put your grade in. And then for those of you that like Excel, you can actually do a lot of the data entry and the graphing in Excel. And I've got a spreadsheet kind of set up for that. And I was thinking about this over the weekend. I think what we ought to just do is there are 4 college students. It takes 4 people to do the project. 4 college students, we'll put them together. And then the high school students, there are 8 of you. So decide what 2 groups you're going to be in. And then if you would sign these, just write down who's in what group before you leave. We'll be all set. Okay? So if you're a college student, get together with, so Brad's big guy sits in the back. Jen's right there. Michelle's here. And then Braden. Where's Braden today? Slacker. Okay. So anyway, we'll get those rounded out. But again, this is what the project looks like. Here are the instructions. I've done this for several years. It's actually quite interesting. It's a kind of a good discovery type of project. So that's what that is. So let's pick up where we left off on Thursday. We were talking about this theorem right here. We were talking about if a function is differentiable, then it's got to be continuous. And we went through kind of a cool little proof that showed that had to be the case. We were talking about making a couple of adjustments. And one of those adjustments is being able to look at a graph, similar to graphs that you've looked at for years, and then changing your mindset a little bit and realizing there's something else I can determine from the graph. Okay, not just what the function values are, but what the slopes are. Okay, so if I look at this right here, all of these function values are positive, but they're all in a line that's sloped downward. So even though the function values here are positive, the derivative would be negative, and that's why we graphed it down here. We figured out that the slope was 1/2 and that sort of thing. If we look at this point right here, even though this point on the curve has a positive function value, in calculus, we're interested in the slope of the curve. How is this graph changing? These are all positive slopes, and then right here, we hit 0 for a slope, and then it kind of turns around and goes down for a second. It decreases for a second. So we're looking at information like that. And we also pointed out that there are 3 different ways a function can fail to have a derivative at a point. And I said you're going to need to know these, because when we find out that a function doesn't have a derivative somewhere, we know that one of these 3 things happened. And one of them is it either comes to a cusp or a corner, comes to a point. And the reason it doesn't have a derivative there when it comes to a point is because the definition of a derivative is a 2-sided limit. It wants the slopes from either side to agree. So it wants us to kind of smoothly come up like this, instead of sharply come up with positive slopes here and then turn around and quickly have negative slopes. Okay? So the slopes on this side would be positive, the slopes on this side would be negative. That 2-sided limit, that difference quotient, they wouldn't agree. Okay? One would be positive, one would be negative. Okay? So cusp or corner, vertical tangent. Please don't say vertical asymptote. That fits in a different category. That's over here. That's where we'd have a point of discontinuity. So those 3 are cusp or corner, vertical tangent, point of discontinuity. Any type of discontinuity will produce a point where the derivative doesn't exist. Ben?
For the cusp corners, it's just one spot.
Right, just right here. Yep, right here at the point. Over here it would still have a derivative, and over here it would have a derivative. And if we go back and we think of this function that we were dealing with right here, what we'd do on this is we'd say, you know, I've got open circles right here on the derivative because the derivative doesn't exist there because it comes to a point. Everybody good with that? Okay. That is great segue into the question that I left you with, and it was this. We went through a proof to figure out that if a function was differentiable, then it had to be continuous. Is the converse of that true? If it's continuous, does that mean it's differentiable? No. Can somebody give me a counterexample? Jump one. Any one of these right here. These are continuous, but they don't have a derivative everywhere. okay, where it has a vertical tangent or where it comes to a point. This example that we were just looking at. This is definitely continuous. It's just a bunch of connected line segments, but look at the derivative. It has a derivative here, no derivative at that particular point right there where it has a corner. Got it? Okay. So if it's differentiable, we know for a fact it's continuous. Just because it's continuous does not mean that it's differentiable. Okay? So the answer there is no, it's not. And we can explain and give a counterexample. Anything that has a cusp or a corner, those are pretty easy examples. Okay? All right. Now, we're going to do some reasonably heavy arithmetic here for just a second. You've got some problems on your assignment where they say find the derivative. Okay, so it says if you're given that f of x is this rational function, 2x over 1 plus x, find f prime using this definition of the derivative. Okay, so here's what we're going to start off with. We're going to start off with f prime of x is equal to the limit as h approaches 0 of, and check my arithmetic here, make sure I don't make a silly mistake. I'm going to plug in an x plus h. So this is going to be 2 times x plus h over 1 plus x plus h minus f of x, which is that rule right there, all over h. So I'm literally just plugging in x plus h into that function, putting it here, subtracting that function right there, and putting it over h, just representing that expression right there. Okay, now for the time being, I'm going to take the limit off. I realize I can't evaluate any of this by substitution because I get a 0 in the denominator. So I'm just going to do some work here. Yeah?
Is that an x prime? On the f of x equals to x over 1 plus x?
Oh, no, it's a comma. Sorry. Yeah, that would be pretty wild if that were a prime. Okay, we'd have to call this Calc 3 or something. Okay? Good there? Okay, so this is 2x plus 2h over, this is 1 plus x plus h minus 2x over 1 plus x. Okay, that is one entire factor, and that is one entire factor. There's not much I can do about that. So I'm going to simplify this complex fraction, and I'm going to do that by getting a common denominator. This one needs a 1 plus x. So I'm going to multiply both the top and the bottom by a 1 plus x. This one right here needs a 1 plus x plus h. So I'm going to multiply the top and bottom by 1 plus x plus h. So that's going to give me, let's see, my common denominator is 1 plus x plus h and 1 plus x. And then my numerator here is I'm going to go ahead and distribute this through. This is going to be 2x plus 2h. Then it's going to be plus 2x squared. Then it's going to be plus 2xh. Doing okay there? Then be careful here. Every one of these difference quotients has a difference in it. It's got a subtraction problem in it. People tend to make mistakes with subtraction, especially when we've got these fractions and everything. So I'm going to make sure I distribute a negative 2x through to each one of these. So that's going to be a minus 2x. That's going to be a minus 2x squared. And that's going to be a minus 2xh. And then don't forget, all of that ugly stuff is still over h. Okay, do you see why I said it's algebra that screws people up? This is not hard, but it is tedious, and if you don't know the rules and you're not keeping track, you're going to make mistakes. Okay, let's go through and let's see what I can simplify here. I've got a minus 2xh and I've got a plus 2xh, so I can cancel the two of those off. I've got a minus 2x squared and a plus 2x squared, so I can cancel those off. And I've got a 2x and a minus 2x, so I can cancel those off. So this is awesome. Take a look at what I've got here. What I've got in the numerator is just a 2h over 1 plus x plus h, 1 plus x over h. Now, this should be, but again, this is an algebra concept, this should be easy from here on out, but for some reason people make mistakes. This is still a complex fraction. It's this fraction on the top divided by, could we make that a fraction on the bottom?
Yeah.
Sure, put it over 1. Okay, if there's a fraction in the problem, you're much better off thinking of everything as a fraction, even if it's not written that way. So we're going to write h as h over 1. We're then going to flip that over and we're going to multiply. So here's what I've got, times 1 over h. And then again, just keeping track of some rules of algebra. These are two rational expressions. They're both completely factored. I can cancel this h with that h, and I end up with this. Okay, now I'm going to bring the limit back. So f prime of x is equal to the limit as h approaches 0 of, I've got a 2 on the top, and I've got a 1 plus x plus h, and 1 plus x in that denominator. So what does the 2 on the top as h approaches 0, what does it get close to? 2 doesn't have an h in it, so it's just a constant for all intents and purposes. Same thing with this 1 plus x. There's no h in it, so it turns into a 1 plus x. So we've got a 2 here, a 1 plus x here, and what does this turn into? A 1 plus x. So what I get is a 2 on the top, and I get a 1 plus x and a 1 plus x on the bottom, so I get a 1 plus x quantity squared. That right there is the derivative. Yeah. This h right here? Right here? Oh, because it's the limit as h approaches 0, so that approaches 0. So it's just 1 plus x plus 0, basically. Yes, exactly. Good? Okay, stop and think about this for just a second. That probably took 4 minutes or so, maybe 5 minutes. Okay, but what we just did is on this nasty graph right here, it's a rational function. We're going to have vertical asymptotes. We've got a horizontal asymptote. We've got a point of discontinuity, which, by the way, where is the point of discontinuity? At x equals -1. Where does this derivative not exist? At x equals -1. You can't plug a -1 into that. Okay, that function right there, right here, this is f prime of x. That will tell you the slope of the curve anywhere on that function. It would take a lot of pre-calculus work to produce that graph. In that much work that we just did on the page right there, that function will tell you the slope of the curve, the exact slope of the curve, the instantaneous rate of change for that function anywhere. So you want to plug in 5,000, plug in 5,000, see what the slope is. You want a -2, plug in a -2. It'll show you the slope at -2. And you've done the work to find that derivative just once. Okay? All right, any questions there? Okay, so again, please make sure that you're careful when you're doing the arithmetic. That's normally what screws people up. Let's take a look at this one right here. We're given a function y equals x cubed minus 2x minus 5, and it wants us to find this. Okay, and again, I introduced this notation last time. It wants us to find dy dx, which literally means the derivative of y with respect to x, the derivative of y with respect to x, and it wants us to find that at x equals positive 1. This little vertical bar with a little subscript x equals 1 means evaluate that at x equals 1. So when we're done, plug in a 1. Or you could use those techniques that we learned in the last chapter where you actually do f of x minus f of 1 over x minus 1. Or you could do f of 1 plus h minus f of 1 over h. Take the limit as h approaches 0, take the limit as x approaches 1, and go at it that way. Okay, I like it a lot better doing it in general, so that's what we're going to do here. So this is what we've got. We're going to find y prime, which is the same as dy dx, meaning the derivative of y with respect to x, by finding the limit as h approaches 0. Follow along here. X plus h cubed minus 2 times x plus h minus 5 minus all of this stuff. Again, please put these in parentheses, especially when there's more than one term. Just get in the habit, even if there's only one term, it's a good idea. So this is x cubed minus 2x minus 5 all over h. Any questions? Okay. The hardest part on here is this right here. X plus h quantity cubed. If you know the binomial theorem or you're familiar with Pascal's triangle and all that sort of stuff, you might be able to figure it out pretty quickly. I'm going to take 2 of these and multiply them together. you get a perfect square binomial. This is what you get. And then I'm going to multiply it by x plus h. Okay? So if I square x plus h, I get this, and then I need to multiply it by one more. So here's what I end up with. So again, I'm just going to draw an arrow here. We're going to leave off the limit for the time being, and this is what we get. We get x cubed plus x squared h. Then we get plus 2 x squared h. And then we get plus 2x h squared. Then we get x h squared, and then the last term is h cubed. That by far is the hardest part of the whole thing. That is just this one right here. I'm going to go ahead and do a little bit of combining terms here. This is going to be x cubed. Got that one. These two are like terms, so this is 3x squared h. This is 3xh squared. Notice the symmetry here. And that's an x cubed. And then we'll write down this stuff right here, because all of this stuff is pretty easy to do. This is going to be minus 2x minus 2h minus 5. Then I have a minus x cubed, a plus 2x, and then I have a plus 5. And all of that stuff is over an h. So let's run through and let's take a look at what we've got. Okay, we doing okay? All right. You'll notice that I only have 2 x cubes, and look at this. X cubed minus x cubed, done there. I've got a plus 2x and a minus 2x right there. I've got a plus 5 and a minus 5, so we're in good shape there. Now, have you noticed a pattern in all of these things as we've been going through and doing them? You noticed what happens? Yeah. Everything has an h in it. So what I'm going to do is I'm going to go ahead and do this in one step. I'm going to take an h out of each one of these. If I take an h out, I'm left with 3x squared. I'm left with 3xh. I'm left with h squared, and this would be a minus 2, and that's all over h. Okay, take a good look at that. Did I make any algebra mistakes? I mean, this is a lot of calculations just for one problem. Good there? Again, they all have an h. I've factored that out. I get to cancel it off now, so that h cancels with that h. And now I'm to the point where I can bring this back and I can say, look, dy dx should be the limit as h approaches 0 of this expression right here. 3x squared plus 3xh plus h squared minus 2. And then I look at that and I think, well, if it has an h in it, that's the variable in the limit. So that's going to change. Anything that does not have an h in it, no matter how ugly it is, we can think of as a constant. So this is 3x squared. What's its limit as h approaches 0? 3x squared. This one, 0. This one, 0. And this one, negative 2. So we'll go through and put all those together. And here's what we've got. We know that dy dx is 3x squared minus 2. That is the derivative of y with respect to x. And then all we want to do now is, it asked a specific question to begin with. It said, evaluate that derivative when x is equal to 1. So if I plug in a 1, I end up with a 1. Okay, think for just a second. What does that tell us about the curve? At 1, it has a slope of 1. Okay? Now, could we figure out what the function value is there? Because that's a pre-calculus question. What do you get if you plug in a 1? 1 here, minus 2, minus 5. So that would be 1 comma negative 6. So here's what we know. It's at 1, negative 6. It's like that. That's all we know, in addition to has a slope like this. So if we were to graph this and we were to find the point 1 comma negative 6, we should see that the graph is sloped upward about like this. Not like this, not like this, definitely not like this, because that's a negative slope, but about like this. Okay? So maybe it's got to, curve something like that. We could graph it and we could see, but we know for a fact it's going to have a slope of 1. Okay, any questions? Okay, if you've got your calculator, um, grab your calculator. If you don't, you can just watch, because here's what we're going to do. We're going to graph this function in a specific window. So I'm going to type that function in here. So it was x cubed, right? And then minus 2x, and then minus 5. And it says graph that in the window -4 to +4 and -18 to 8. So I did this ahead of time just so we could have a decent window to graph this in. We wouldn't have to search around for it. And then -18 to 8. So I'll hit graph. Okay, and let's see, if I hit trace and I go to 1, okay, there's the function value. Okay. So if I looked at that and I said the slope, I would think the slope looks something like this. Okay. Is it positive? Does it look like a slope of 1? Can somebody tell me why not? Yeah. The scale's different on each one of these axes. Okay. So if we were to do something like this, I'm going to hit zoom decimal. Well, this is a nice squared off window, okay, but the problem now is it doesn't go down to the point that I'm interested in. Okay, so I'm going to change this and we're going to go down. I'm going to go down 4 and down 4. You can do arithmetic right there. Okay, now I'm going to hit trace and I'm going to hit 1 and it's going to hop right to that point. Okay, now if we look at that, does that look like a slope of 1? Does that work? So now we can draw on it. That looks about right, doesn't it? Okay. All right. It says find the equation of the tangent. What do you need to do to find the equation of the tangent at 1? Yeah, we already got the point in the slope, so this is a piece of cake. Y minus, y value was -6, so we're going to do +6. Slope was 1, and x minus 1, and there's the equation. If I move that over to the other side, I get y equals, and I'm going to write it this way. I'll write the 1, x plus, or x minus 1, and then this would be -6. And I'll grab the calculator, and I'll go ahead and put that in. So we've got the same graph. There's my slope. There's x minus the x coordinate of the point that it goes through, and then plus the y coordinate. Or sorry, plus the y coordinate, which in this case is negative. If I hit graph, shows up. Okay, let me slide this over. Looks exactly like it ought to, right? Okay. Any questions? Okay. All right. Now we get to do some interesting stuff. Yeah.
Is it alright if we just keep it in that form if you want it to?
In this form right here? Yeah, point slope form is fine. The nice thing about this is you can put it into your calculator without doing too much manipulation. If you think of it this way, though, if you kind of move that y1 value over to the other side, later on in this chapter, we're actually going to see a nice application for that. Or maybe it's in chapter 4 in this book. It's called the linearization. They're kind of cool. Okay? All right. So now what we're going to do is we're going to look at some graphs. And again, this is helping you make that transition in your mind. Don't just look at the graph and think, what are the function values? We're talking calculus now, so we're thinking, what are the slopes? So in each one of these examples, you notice that the y coordinate is labeled as y, and then down here it's labeled as y prime. So these are all functions. These are all derivatives. Or if we set it another way, these are graphs, and these are slopes of the graphs. So let's look at this one right here. And I know we already kind of did this one. We don't know what function that is. Maybe it's x squared. It kind of looks like a parabola. Okay? But we want to look at this and we want to think, what do all of these slopes have in common? We're thinking calculus now, not function values. We're thinking calculus. We want to find derivatives. What do all of these have in common? Okay, so negative slopes. What's the derivative here? 0. And then what do these have in common? They're all positive slopes. So down here, we're looking for something that starts off negative. That starts off negative, and that starts off negative. Hits 0, and then turns positive. So we're looking for something that has values that are negative, 0, then positive. Which one is it? Got to be B. Okay? Let's look at this one. What do these slopes all have in common? Not function values, slopes. They're all positive. And they start out really big, and then they kind of get closer and closer to 0. And what is it right here? 0. And what do all these have in common? All positive. So we're looking down here for derivatives, slopes that are positive, then 0, and then positive. Really big positive, shrinking down to 0, and then gradually getting bigger and bigger and bigger. Which one's it got to be? Got to be A. Okay? Big positives, small positive, smaller positive, really small positive, all the way to 0, and then same thing on the other side. And notice how it's symmetric, just like that graph was symmetric. Okay, let's take a look at this one. Okay, let's run through and do this. Okay, if you struggle with this, one of the easiest places to find slopes, even if it doesn't have a scale on the axes, is where the slope is 0. So let's do this. There's a 0. There's a 0, there's a 0, there's a 0, there's a 0. Okay? Of the two that are left, which one crosses the x-axis 5 times? This one right here. This has got to be it. Okay? But let's check and see. Let's see if this works. What are these right here? Positive slopes. Then they're negative. Then they're positive. Then they're negative, and so forth. So we start out positive, hit 0, then go negative. Positive, hit 0, then go negative. Hit 0, then go positive. Hit 0, then go negative, and so forth. So you see why that's got to be the answer right there. Any questions? Of course, by default, this one has to match up, but let's check and make sure. What about all of these slopes? Okay, these are all negative slopes. Now watch, please. For some reason, because this hits 0 right here, that screws people up. All of these slopes, all the way along here, all the way till right there, they are all negative slopes. 0 for a slope here, here, and here, in those 3 places. Okay, right here, positive slopes, negative slopes, and these are all positive slopes. So we're looking for something that starts off with negative values, hits 0, positive values, hits 0, negative values, hits 0, and then continues being positive. Negative here. Negative slopes here, negative values on the derivative. 0 right here, 0 on the derivative. Positive slopes here, positive on the derivative. Okay? Do we get the idea? Any questions? Okay. Great. Then any ideas on what this means or this means? Oh, very good. Okay, so these are both notations for the second derivative. Okay, this is said f double prime. Okay, and I'm not going to write this one. This other one is the differential notation. This is said d squared y dx squared. D squared y dx squared. Okay, and what it means is find the second derivative of y with respect to x. Find the second derivative of y with respect to x. Okay, and Peter, how did you say it again? Slope. So slope of the slopes. Okay, we're talking graphically speaking, or we could say, and I'm going to write it this way, rate of change of rate of change. You could continue going. Yep, we could find what we could find what we call higher order derivatives. First and second derivative are used a whole bunch, and we're going to study those a lot. Third derivative, fourth derivative, and things like that. We use those occasionally. We use them a lot more. You'll use higher order derivatives in Calc 2 quite a bit. Okay, we mostly confine ourselves to the first and second derivative, and we'll talk about why here. So we've covered all of the ideas. So basically the idea here is find the derivative of once, get some new rule. Like if we were to find the derivative, the second derivative of this, we'd do the limit as h approaches 0 of 3 times x plus h quantity squared minus 2 minus, we'd run through that difference quotient again. We'd kind of like start the process over, okay? It's not a fun thing to find those by hand, okay? And luckily you don't have to do that by hand very much until we learn in these next couple of sections some rules that will make this a little bit easier. So here's what we've got left. I'd like to take a look at problems 6 and 7, or example 6 and 7 in the textbook. And then I'd like to try problem number 44. It's actually in the section. So let's run through and let's take a look at this. And I just want to point out these things right here. So here's what they did. This is an example out of the textbook. It says we're given this function right here, and we want to interpret f double prime, or in other words, the second derivative. So it says in example 2 in the textbook, they found that the first derivative was this. Notice it's very similar to the example that we just did, so you've got two things that you could look at. If you're going to find the second derivative, that means you find the derivative of the first derivative, the slopes of the slopes, or the rate of change of the rate of change. So notice that they use the same difference quotient, but now instead of using the original function as the function, we're using the derivative as the function. So we've got 3, x plus h quantity squared minus 1. There's f prime, with the x plus h plugged in, and there's f prime. And then they go through and they do all the arithmetic. Notice the arithmetic is relatively simple on this one, and they end up with this right here, okay? So this is the function right here. This is the first derivative, or this is f prime, and this right here is f double prime, okay? And here's what it says. Okay, it says something similar to what Peter said. It says we can interpret f double prime as the slope of the curve f prime. Well, if that represents the slope of the original function, we're finding the slopes of the slopes, okay? So if we look over on this picture, and one thing that this book tends to throw everything all together, and it can be a little bit confusing. So let's take a close look at this diagram and let's see if we can figure this out. Okay, it says this is the function, the blue one's the function, okay? This pink one is the derivative, there's the first derivative, okay? And here is the second derivative right here. And you kind of have to look at these one at a time. So let's do the same thing we did before. We're going to take a look at the blue one right here. Let's look at the original function, and let's just see if we can match this up again. Again, what I'm after here is find where it equals 0, because those are really easy. So right here and right here. That's where the original function has a slope of 0. What do we notice about all of these slopes right here? They're all positive. And notice that on this one, we've got all of these positive values here. What do we notice about all of these slopes right here? They're all negative, and they start off very shallow negatives, get fairly steep, and then shallow off again. So that's this part of the derivative. And then again, right here, slope is 0 on the original function, and then they get more and more positive. So we've got this right here. Okay, now let's look at the red graph, and then let's think about what are the slopes of the slopes? What's the derivative of the derivative? Or in other words, what's the second derivative? So we can kind of ignore, we've moved past the original function now. Now we're looking at this as the function. And again, what's the easiest thing to identify? Where the slopes are 0. Slope is 0 right here. That's why on that one, we've got a value of 0 on the second derivative. What do all of these have in common? They're all negative slopes, and these are all positive slopes. That's why it's negative values here on the second derivative and positive values here on the second derivative. Okay? Tons of information put into one single graph. But can you see how they're related one to the next? All we're doing is keeping track of slopes of the original function. There's my first derivative. Slopes of the derivative. There's my second derivative. Okay? Slopes of the slopes or rate of change of the rate of change is okay there. Okay, any questions? Yeah.
I'm not trying to be, but we'll use the second derivative. I think that getting the first derivative, that's cool. You can find at any given point velocity. How is the second?
How would that help us? The short answer to that is if you take a look at the graph, okay, and if you don't get this, we're actually going to spend 2 or 3 sections talking about these ideas of what the derivatives tell us about the graphs. Okay, you see all these right here? See how the second derivative is negative here, and the second derivative is positive here?
Yeah.
I want you to take a look at the original graph, and I'm going to draw it in 2 pieces. Okay, so we're looking at this and these right here, and we're looking at, let me change colors here, this and these right here. Look at the original graph. Do you notice anything about the difference about the stuff that's shaded in yellow versus the stuff that's shaded in blue? We'll open this up to anybody. Does anybody notice anything interesting about what's shaded on the original curve in yellow and what's shaded in blue? There's a distinct difference. Does anybody see what it is? Okay, rotated around. So this one is, okay, this one is cupped downward. Okay, if it had a cup to it, it's cupped downward like this. Everybody see that? And what about this one here? It's cupped upward. And you can use the second derivative to tell you about the shape of the graph. We call it concavity. So we can tell which direction the graph is caved. So if we were to look at, remember this example right here? See how parts of this, that's cupped upward, and then these other parts, these are cupped downward. Okay, you can actually use the second derivative to tell you that. You don't have to graph it. You can tell that it's got to be cupped upward, shaped, curved like this, and curved downward like that, just using the second derivative. Okay? That's a graphical representation. And now let's talk about a different one. Okay? And it says this, and this should be something that you're familiar with because we've mentioned this several times. If S of t is a position function, we've already dealt with position functions and we found the rates of change of position. You'll remember that when we found rates of change of position, we got velocity. So if you find the derivative of position, you get velocity. The derivative of position is velocity. Well, what happens if you find the derivative or the rate of change of velocity? Somebody who's had physics? It's right here. You get acceleration. Okay? So if we start off with S of t, that's a position function. If I find the derivative once, that's a velocity function. So you can go from position to velocity just by finding the derivative once. And if you find the derivative a second time, or we could also call that the first derivative of velocity, you get acceleration. So if I have a position function and I find the derivative once, that gives me velocity. So this is position. Find the derivative once, I get velocity. Find the second derivative of position or the first derivative of velocity, then I get acceleration. Okay? So there's a physical interpretation of the second derivative. Okay? And you'll notice the notation here. Acceleration is the first derivative of velocity, second derivative of position. If we write it in Leibniz notation with those differential, acceleration is the derivative of velocity with respect to time or the second derivative of position with respect to time. So I suppose we could keep going, okay, and we could get what we call, well, let's see, F prime, F double prime. This is F triple prime, F triple prime. These are called higher order derivatives. And that, of course, would be the third derivative and so forth. We normally don't, once we get to 4 derivatives, we normally abandon the prime notation and we'd write something like this. It's not an exponent, it would just mean the 4th order derivative. Okay, so you'll notice that they have the nth order derivative of y, the nth order derivative of f, or d to the nth y, dx to the nth, yeah. No, we'll talk about it in just a second. Okay, so everybody okay with the notation? Okay, so let's talk about if you were to find the third derivative and you had a position function, it's actually called the jerk. Okay, so the third derivative of position is the jerk. So the rate of change of acceleration. So how fast the acceleration is changing is called the jerk. I mean, you can kind of imagine why. When you're feeling an acceleration, so if you're in the car and somebody is accelerating in a positive direction, speeding up, or negative acceleration, some people call it deceleration, slowing down, you get kind of thrown back and forth. Well, what if that was happening at a really rapid pace? You'd feel pretty jerked around, right? Yeah. Impulse? Okay. Mm-hmm. It could. I've never heard that. I've never heard that, but that could very well be. One interesting application here is everybody's seen on their car, if you look at the tachometer, it has a red line. If you think about the way the pistons and the parts in there move up and down and back and forth, every time it goes up to the top of a stroke and then down, it's changing direction and it's doing it very quickly. If you do it fast enough, the jerk can kind of help explain why an engine would just fail. I mean, it will throw a piston or a rod or something like that because it can't change accelerations that quickly. Okay, when we get into more of chapter 3 and start talking about how we find derivatives of trig functions, because trig functions are what we'd use to represent that circular motion, then we can talk more about that. Okay, any questions there? Okay, let me just see really quickly. Yeah, here's example 7. So this is the same function right here, and we found that the first derivative up above was 3x minus 1, and that the second derivative was 6x. So think about finding the third derivative of that. Well, if we're dealing with a function 6x, what's the rate of change of 6x? Yeah, it's a line. The slope is always 6. That's why the third derivative would be 6. If 6 is the function we're dealing with, it's just a horizontal line. What's the rate of change of that? 0. Okay, so that's why the fourth derivative would be 0. You could do each one of those graphically, or you could go through the limit of the difference quotient on each one of them. You're going to end up with the same thing. We just kind of shorten it on that problem, just do it geometrically. Okay. Any questions? Okay, so again, I said this book likes to throw everything all together. So this one, what I did here is I took the graph that they gave us and broke it into a couple of different parts here. So this is the black one. This is part D. This is the, I think it looks green. That's part C. B is this guy right here, and A is that one there. And what we want to do for this is it says the figure shows the graphs of F, F prime, F double prime, and F triple prime. So I've got a function and then 3 of its derivatives, but it doesn't tell me which order they go in. So we want to figure out which one's the original function, and then which one is the first derivative, second derivative, third derivative, and so forth. Okay? Any ideas? Ben?
Well, the last one, we know if we would find the f prime of the last one, of A, it'd be a straight line. And none of them is a straight line, so I don't have to do the graph.
Very good. This one would have to go from negative to 0 to positive. And it does look like it would be a straight line, although this one, if we've got negative, 0, and positive, doesn't this fit the bill kind of right here? You're right. I'm just arguing for the sake of argument. Okay, so you do have to be a little bit careful with that one.
Couldn't we just estimate like what power would be raised to and say X in order?
If we knew how to quickly find derivatives of power functions, we could.
This would be like X squared and X to the fourth.
Yep. X squared, x cubed, x to the fourth, x to the fifth. They probably have something to do with each other. In fact, they do, and we're going to show that, I believe, in the next section. Okay, but all the tools that we've got right now are just graphically. Okay, so all of these are good observances. Okay, but go ahead.
Wouldn't you be counter and say that the graph D has two zeros and the only one that matches up is C?
Very good. Okay, I've got a 0 here and a 0 here. Positive slopes, then negative slopes, then positive slopes. So I'm looking for something that has two zeros, which this one does, positive, negative, and then positive again. So this one is the derivative of that one. Okay, could we keep going? How many zeros here? 1, positive, 0, or yeah, positive, and then, yep, so it's going to need to all be positive. So can this one, what's that? Oh, sorry. Negative slopes, 0, and then positive slopes. Thank you. Okay. So that would work out here. So it looks like this one might be the original function. This is the first derivative, and this is the second derivative. Let's just make sure that this matches up. Positive, 0, positive, positive, 0, positive. So we're thinking f, f prime, f double prime, and f triple prime. Okay. Has anybody heard of a tool called Snap-a-Shot? It's like a little screen snapshot software. It's pretty cool. Doing this project in 4 separate pieces, or this part in 4 separate pieces, is a lot easier than trying to look at this and keep them straight. Okay, so don't underestimate. I did a little bit of work for you here. Don't underestimate that little bit of work. Just separating those 3 or those 4 is so they're 4 separate graphs that you can look at. Really helps make it easier to understand. Okay, so if you need to do that as you're going through and draw a couple different pieces, totally acceptable. Okay, can really be helpful. Okay, any questions?
That's the best way to do it is to do it here, is looking at all the zeros and then
Finding where the slope is 0 and then breaking it up into, okay, it's positive over here, negative over here, and so forth. That really, I think, is the best way to do it. And it's not that we do a ton of this. They're just kind of getting used to the idea that, notice there are no scales on the axes. You're literally looking at it, and the only thing that you could figure out from this is really a calculus question. Tell me about the slopes of these curves and how they're related. Okay? Right. Anything else? Oh, that's a record. We're 2 minutes early. Okay. All right. Have a great day. If you've got questions, feel free to stick around.